Okay, good afternoon, students. So, today this is our first class. This is digital signal processing. Okay, so the word itself, digital signal processing. So, the processing means what we can say is processing is nothing but the some kind of modifications or extractions of a signal. So, what we are doing here, we are doing some modification or extraction about what, so we are doing some process on the signals. So we are doing some process on a signal, and how these signals are, so these signals are basically in digital form. So this is nothing but a digital signal processing. Okay, so you might have know about the analog signal and digital signal. So So basically, this course, digital signal processing, is focused on the digital signals. Okay. So there are many methods to do the extraction what we want for our particular application. So there are many types of processes which we can do, and we can get whatever output we want in our application. Okay, so here we are basically focusing on the digital signals. So we are processing these digital signals, which are basically digital signals are basically the indexed by the integers. Now, later in this class, we will see what is the digital signal, what is the analog signal, that we will see. But in a brief introduction of this course, this the title of this course, we can say that we will process these digital signals which are indexed by the integers. Okay, integers which are discrete in their independent variable. Again, the term independent variable and dependent variable for a particular signal, that also we will see how which variable is independent, which variable is dependent, that we will see later in this course. Okay. Now, for example, when we talk about the processing of digital signal, so we can take the example of audio signals. Okay. Now, there are many type of signals. You will find 1D signal, 2D signal, and 3D signals. And again, there are many higher dimensions are also there. Okay. But in visibility, we all familiar with the audio signal, then image pictures, which is nothing but the 2D signal. Then the video, we can talk about the video or volume elements, they are in a 3D form. Okay, again, there are many higher dimensions form where we can apply this processing. Okay, now in digital signal processing, when we talk about the digital signal of audio signal, when we talk about the audio signal, so we take some sample and we will do some process on that sample, and then this process will give us some output. Okay, now in this course, basically our focus is nothing but the one dimensional signal. We will only focus on one dimensional signal, not 2D and 3D. So we will not talk about the image picture and the video. So we will talk about only the signals, the 1D signal. Okay. Now, why there is a digital signal processing? So we are having analog signal processing also. But why there is a digital signal processing? So these are some highlights about the analog signal processing. Now, in analog signal processing, basically we process the continuous time signal. We process the continuous time signal. Okay. Now, for example, the audio signal, the speech, we can say this is continuous time signal. Okay. Now, when we apply some process on this continuous signal, so basically this signal, the information of this signal where we store, that will be very vague information we have to store in the hardware, and that will need more amount of the hardware capability. So basically the analog signal processing is not economical, we can say. So this analog signal processing is not economical when we talk about the hardware and even in the software. Okay, therefore, most of the time we use the digital signal processing. This is the drawback of the analog signal processing. Okay, now in digital signal processing, basically what we do sampling of the signal. So we are having continuous signal in real time. Basically, there is a continuous signal. So these all this term we will uh, familiar you will familiar with this terms. What is sampling? What is discretization? Aliasing? That type of terms will be there in this course. Throughout this course, we will uh, get familiar with this. Okay, just to know about the general introduction of this course, I will just say only the sampling. But basic meaning of sampling, you can understand what is sampling and all. Okay. So in digital signal processing, what we do, we sample this continuous signal. Okay. And we will process after sampling, we will do the processing of the signal. Okay. Now, what is the benefit of doing this? So this is very important in our course, the sampling and processing. Okay. Now, there are many, in detail, we will see how this sampling will be done and how the processing will be done. Now, what is the benefit of this sampling and processing? Okay. So the benefit is that we will get more flexibility to do the process on that particular signal. So this is very important that there will be a flexibility. Whatever signal we are having in real time, so we are having more flexibility to work upon that signal. Okay, so we are having to do the different kinds of processing on that signal. We can do different kind of process. Okay, so this is nothing but the flexibility of the kind of processing. Again, there will be a richness in the operation. If we sample it, we will get the richness in the operation, and this will be the robust one. Okay. Now, this type of signals, this signal sampling of this continuous signal, these signals are basically the robust signal, flexible, and they are adaptable in nature. Okay, so this is very important advantage of the digital signal. Okay, now with nowadays we are having different kind of high computer. So with the very high computers, very high processors we are having. So nowadays it is extremely attractive. Therefore, this digital signal processing is basically very attractive. Okay, so therefore, digital signal processing is used in many applications. You will find many applications where this digital signal processing is used. Okay, so everywhere you can see the application of this, like in astronomy also it is there, in consumer electronics it is there, in aviation it is there, in security it is used, in medical field also it is used, engineering it is always there. Okay, geophysics also you will see, communication system. Now in finance also nowadays it is used, digital signal processing. Okay, so all these are the application of digital signal processing where it is used. Okay, now in particular application for the particular operation it is used. So these are listed here. You can go through it later. Okay, or you can also tell me some nice application where it is used if you know. Okay, that also you can put it in the chat box. Okay. Now, this is our first lecture. So the objective of this lecture is to basically, in the last lecture, the Rodney sir, he has told you about the course structure and all these things, right? So, in today's lecture, we will go through the definition of the digital signal processing. Then we will see the key difference between the digital signal and the analog signal processing. Then the broad range of DSP applications. Then we will see what is signal, what is system, and we will understand some concept about the linear time invariant systems. Okay. Now, but basically, what is a signal? So signal is nothing but the flow of information. In Okay, so we can say that the signal is nothing but the flow of information. There is some information stored in the signal. Okay, now how this signal is uh, defined? Okay, so this signal is basically measured, the quantity, some quantity we measure with respect to time. Okay, now this time we can say that this is independent variable. Okay, which is on x-axis. This time is independent variable, and there is some quantity here, can be a voltage if there is electrical signal, current we can say on the y-axis. Okay, so many a time independent variable is many a times it is time only. So time is often the independent variable for any signal. And most of the time, whatever signal we are seeing, we will see in this digital signal processing. So we will have independent variable as time only. So you will find the signal with time as an independent variable, which will be on the x-axis. And on this y-axis, there may be any type of uh, signal, that amplitude or if we talk about the electrical signal, then there will be voltage and all this thing. Okay. Now, how to represent this signal? So representation in mathematical form is, we can say, this is x of t. Okay, so we represent the particular signal with some symbol x, and in bracket it is t, means it is varying with respect to time. Okay, so this is basically the general representation of the signal, general representation, and this x can be anything. This x can be anything like voltage, the speech, if it is speech, then it will be the amplitude of the voice and like that. Okay. Now, if you see this picture, this is the one-dimensional signal. This is 1D signal. Okay. Now, we are also having it is not there in the course 2D and 3D signal, but you can see this image, which is, we can say that this is the 2D signal. Okay, this image is nothing but the 2D signal. Okay, now for 1D signal, time is the independent variable. Okay, so 2D signal we represent in the space. Okay, 2D, 3D, even the more complicated dimensions. Okay, so signal is basically the representation. We describe this signal as a function of some variable. Okay, so that variable is nothing but we call as a x of t. Okay, so this is independent variable, that is most of the time it is the time. Okay, so if we are having the electrical signal, then received from the transducer, these are some examples of the signals. Okay, microphone, thermometer, accelerometer, antenna. So from this we will get the signals, electrical signal. Okay, and this electrical signals that controls the process later, that will be used to control some process. Okay, now we are having continuous time signal and the discrete time signal. Okay, and the example of continuous time signal, we can say we are having voltage, current, temperature, speed. These are some continuous time signal. And discrete time signal example, we can say that the daily temperature of the your city, you can say maximum minimum temperature, that is in discrete form. Then sample continuous signal, which is nothing a discrete. Lap intervals in the races, these are nothing a discrete form. We will get information in the discrete form. So that those are the discrete time signals. Okay. Now what basically a continuous time signal and a discrete time signal? Okay. So how we define the continuous time signal? So basically in the physical world, we are having most of the signal in a continuous form. Okay, so this continuous time signal, we can say CT signals. Okay, now how to view these signals? So we can view these signals through a transducer or a device that convert this continuous time signal into the electrical signal, and then we can probably see the particular signal. Okay. Now, most of the time, we can say that the common transducers are basically our ears, eyes, nose, okay, which are very complicated. Okay. Now, the simple transducer, if I want to see the signal voltage from some electrical circuit like this. Okay. Now, what I will do, I will connect some voltmeter here in the circuit. If I want voltage at this two terminal, if I want to see the signal from this circuit, this is just a circuit. So I have to connect this voltmeter here and then probably I can see the signal. Okay. So these are the simple transducer. Now, if I want the voltage of this particular circuit, then I will see with the voltmeter. I can see with this voltmeter. Okay. Now, again, whatever quantity we want to see, so for that we need to connect some transducer. Through transducer we can get the signal, okay, which are mostly in the visible form. Okay, the general representation of a continuous time signal is like this. You will see the signal in like this pattern. Okay, this is just some audio signal. Okay, so this is the continuous time signal. Now, how the discrete time signal is? So basically the discrete time signal, you can see here, it will look like this. So there are time samples on the x-axis. Okay. Okay. So we can write the collection of the numbers you can see here, which representing a signal as a function of discrete variable. And this discrete variable is nothing but this n. Okay. And this signal we represent like x of n. Okay. So the continuous time signal, how we represent continuous time signal? So this is x of t is the representation of continuous time signal, which is nothing but the variable which is changing with respect to time t. In discrete form, it is the variable is changing with respect to this n, which is nothing but a discrete variable sample. Okay, from 0 to, you can see here. Now, what this x of n represent? This x of n is represent the amplitude or the value of particular signal at That is this particular instant n. Okay. Now, therefore, this is a function of n. This discrete time signal is the function of n. Therefore, it is x of n. And it is always there in a square bracket. You have to remember this. And this continuous time signal, it is in the round bracket, x of t. Okay. And always this n is a integer value. That also you have to remember. You need to remember this. These are always integer, like 0, 1, 2, 3, 4, like this. Okay. So the example of this discrete time signal is microprocessor, semiconductor, memory, shift registers, you can say. So where you will get the discrete time signals. Okay. Are you clear with the continuous time and discrete time signals? Is it okay with you?
Yeah, Rita.
Yes, it's okay.
Okay. Okay. Now, basically, we are doing the processing. We will do some process on these signals. So, we basically in signal processing, we have to be transform the signal in order to. So, what kind of processes are there? So, in general, we can say if I want to amplify some particular signal. Okay. So, amplification is nothing but the transformation of signal. If I want to filter output of that particular signal. So the filtration we can do. So filtration is nothing but the process which we will do on the signal. Okay. So we can transform this signal to get in order to get the amplify or filter out the information, or to detect the pattern also we can use the process. Then prepare the signal to survive a transmission channel. That also we can do in the signal processing. To prevent the inferences with the other signal sharing medium, that also we can do in the signal processing. Uh, so there are many ways of processing you will see in the different kind of applications. Okay. So like to compensate for a sensor deficiencies. So all these are there where we can get the transformed information from particular signal. So basically where we get this signal, so signal will come from some system or some network, and then we are processing that. Now to do this signal processing, we also need a method to measure, to characterize, to model and simulate the transmission channels. So all these things we will need for the processing. Okay. Now there are some mathematical tools that split common channels and transformation into the easily manipulated building blocks. Okay, so in detail we will see this methods and the models, all this thing we will see. Okay. Now analog circuit, you know, this is just an analog circuit. Okay. An analog circuit, this is just an example. This is RLC circuit, and you will get this signal from this continuous time signal from this analog circuit. Okay. Now analog, there are many advantages of this analog electronics. So this is basically in analog electronics, we use the passive networks. A passive network means what? So we will be having the combination of resistor, capacitor, inductance. These are the passive elements, energy storing elements. Okay, there may be a filters and this. So all these are the, there may be some non-linear elements like diodes also. So that will be there. Okay. The advantages of this analog electronics is basically they are highly linear over very large dynamic range, and they will be having the large bandwidth in the system. There may be they require a little or no power for the analog signal processing, and there will be a little inferences on the system. So in analog electronics, this thing will be there, but there is a problem. If you want some particular type of output from the system, then in that case you cannot do more process on that particular signal. These advantages are there, but there are not many methods to work upon this analog signal, because analog signal needs very high hardware power. The storage power will be needs to be very high, and the software also uh, some different very high powered software we need to use. So the main disadvantages of this electronics analog electronics is that therefore there is a digital processing. Okay. So uh, in digital signal processing, basically we will be having these devices. Okay. Now, you may be familiar with all these devices like analog to digital converter, digital to analog converter, CPU, DSP, FPGA, all this term. I think these are familiar with you. Okay. Now, what is the advantage of this digital signal processing? So, all these are the advantage. Now, this is also highly linear, but within some limited dynamic range. Digital signal processing, this is also linear, but in limited dynamic range. Now you can apply the complex algorithm in a single chip, FPGA DSP chip. Then the noise you can easily control. This is very flexible, and you can easily vary the parameters of the system through some software. This is also insensitive to the component tolerance, the aging, environmental conditions, electromagnetic inferences. This is very important advantage of the digital signal processing, because this is insensitive to all these conditions. Okay, but in the analog uh, circuit, you will not see. So the some this will be very sensitive to these conditions. Okay, but in this digital signal processing, but there is a discrete time processing artifacts aliasing will be there. It can require a significantly more power. So these are some drawbacks of this digital signal processing. Okay, the digital clock and switching, they may cause interference. Okay, so these are some drawbacks of the digital signal processing. Okay, now broadly, uh, when we talk about the signal, so basically we will get signal from some system. We will get signal from some systems. Okay, now what is system? System is what? So this is general block diagram of the system, like in square bracket. So this is the some function of the system, we can say f of x. Okay, some with some variable we can define the system, but in general represent how we in general form we represent this signal and system like this. Okay, so we will be having some input to the system, like this. And after passing this input through this system, we will get some output y of t. Okay. Now this both are the signals. X of t is also signal, and in the output form we will also get the signal. Okay. So this signal is basically what? This signal is a description of how one parameter varies with another parameter. Okay, for instance, the voltage changing over time in electronic circuit. Okay, or when we talk about the image, it will be the brightness, dullness of the image. Okay, so this is nothing but the description of the parameter, just changing with respect to time. Okay, now what is system basically? So here, this is continuous system, we say. This is the discrete system, we say. Okay, now continuous system, you can see here, this is x of t. Discrete system, this is input signal is x of n, that you need to represent very carefully. X of n in a square bracket, y of n in a square bracket, and signal also is represented with some sample. It is not like this continuous time. Okay. Now system is nothing but we can define this system as this is nothing but any process that produces an output signal in response to an input signal. That is how we define the system. Okay. So system is nothing but the process. Okay, which will produce an output signal. So this is how we can define the system. Okay. Now, uh, there are some properties of the signals. Now, the most of the time, you can see this signal. The properties are very important properties are the periodicity of the signal, or whether the symmetry of the signal. That also we need to check. Okay. Now, signal with this symmetry and the periodicity, how to define the periodic signal? Okay, so this continuous time periodic signals, we can represent like this. And you can see this is the periodic signal in continuous time. This is basically the general description of the signal. So what is there? You can see the repeating sequence of the signal. Okay, so this is the repeating signal with respect to time. Now this is the time of one period. Now from this 0 to up to this, you can see this is the pattern of the signal, and again this is repeating after this t. Okay, so this t is nothing but the one time period, and this will be continuous till the end. Okay, so the continuous time periodic signal we represent like this. X of t is nothing but x of t plus t, and this capital T is basically time of one period. Okay. Now the how we can say the discrete time signals. So discrete time signal, periodic discrete time signal are like this. So we can represent this in this form. X of n, x of n plus capital N. Again, this capital N is nothing but the time period for one cycle. The sample, the size of one time period ka sample. Okay. Now again, we can do many transformation of this on the CT and the discrete time signal DT also. So that also we will see later on. Now, Again, whether this signal is even signal or odd signal, that also in some cases we need to check. Okay. Now, how to check the whether the particular signal is even signal or the odd signal? So, this in continuous time form, if this signal you can see here in this graph, what you can see here? So x of t is equal to x of minus t. Suppose here I can say time of 1 second and time of minus 1 second. So you can see the same value, same amplitude value on the both right hand side and the left hand side of the of x of minus t. If you get, if it is there, then this is nothing but the even signal. Same in case of the discrete form also. Okay, x of n is equal to x of minus n. Then the signal is even signal. Now, what about the odd signal? If the signal at particular time t1, if I say, if you are getting some value of 1, okay. Now, if, and this is suppose minus t1, and you are getting the same value on this negative axis, then this signal is the odd signal when x of t is equal to minus x of minus t. Then that case, it will be a odd signal. Okay, so again, what are the benefit of this even and odd signal? That also we will see later. But in general, you should understand what will be, how it will look like. So you can see here, uh, along the x of t axis, you will see same pattern on both the side. Okay, so this signal, this type of signal will be the even signal. Now, along the x-axis, time axis, if this is same, this similar pattern, if you see, then it will be the odd signal, negative of this. If you see around the time axis, if on the positive side, it is like this, and on the negative side, it is minus of this positive side, and then you can say this type of signal is the odd signal. Okay, so by looking at the signal also, you can say whether the signal is even signal or odd signal, or there may be a mixture of even and odd signal, that also will be there. Okay, so we will see this later, how one particular signal is represented in the even and odd form. Okay, now the properties, if we say the even and odd signal, what are the properties of even and odd signal? Basically, any signal we can express as the sum of the even and odd signal. This is very important. If I'm having signal like this, then this signal is basically the addition of these two signals. If we add these two signals, then we can get the signal like this. So any signal we can express in the sum of the even and odd signal. Okay, or we can split some particular signal in even and odd form. Now here you can see here, by looking at the signal itself, you can see this is the even signal, and by looking at this signal, you can say that this is the odd signal. Okay, and if you add both these signals, even and odd, you will get this the final signal. Okay, right? So this x of t, some signal x of t, we can say this is the combination of x even signal. X even t is nothing but the representation of even signal. X odd t is nothing but the representation of the odd signal. Okay. So x of t we can write like this: x even t plus x odd t. Okay. Now, how to get the, if I'm having the signal like this, then how to express this signal in the even and odd form? So there are these the term. So if you apply this formula, you will get the even signal. Okay. How we can get even signal? Which is x of t plus x of minus t by 2. This is how we can get the even signal. If you apply this formula on this signal, then also you can get the even signal. Okay. Now to get the odd signal, we can apply this formula. To get the odd signal, x of t minus of x of minus t by 2. Now how to get x of minus t? If I'm having x of t, then how to get x of minus t? You just need to uh, time, you have to take it as a negative, right? So x of t, x of minus t, we can get the we can express this in terms of even and odd signal. Here you have to see this is amplitude 1, but in the even signal you can see amplitude is half. Please carefully see the representation. Okay, the expression of even signal is with the amplitude half. Odd signal is also having amplitude half. And the real signal is having amplitude 1. Okay, this is shown in the discrete form. Okay, and this is written in the continuous form, but you can say that this is nothing but x of n is equal to x even of n plus x odd of n. Okay, like this you can say in the discrete form. Okay, so this signal is nothing but what? This is the unit step signal, because we are having unit values on the positive axis. So this is in continuation. Okay. So how we represent the unit step signal? Like this: 0, and this is amplitude 1, and it is on the positive side, it is going on. So this is the representation of the unit step signal. And this we can decompose in the even and odd form. Okay. So this is just an example of this extraction, how we can get even and odd signal. Okay. Now, basically, we are having these systems on which we are uh, giving some input, and we are getting some output. Now, how these systems are? So we are having system having x of t as an input, and we are getting y of t of input. Okay. Now, these systems can be time invariant systems. Okay. Now, there are many types of systems, but in our case, we will be focusing on the time invariant systems. Okay, this is also called as the shift invariant systems. Now, how to define this time invariant system? So time invariant systems are the systems, one, where a time delay is nothing but the shift in the input sequence causes an equivalent shift or equivalent time delay in the output sequence. Okay, sequence, we talk about this, we are saying this is sequence because we are talking about the discrete uh, input signal. Okay, so I can say this is x of n and this is y of n. Okay, so please understand what are the time invariant systems are. So the time invariant systems are the systems where a shift in the input sequence causes an equivalent shift in the output sequence, system's output sequence. Okay. Now, some system, suppose I'm having some system here, which I say this is G of S, and I'm applying some output X of N. Actually, we should use here square bracket, and it should be Y of N. We are getting output Y of N. Okay. So this system G of S, this is just a representation of the system. So this particular system basically provides output Y of N for a given input X of N. Okay. Now, this particular system to G of S to be time invariant. So how we can say that this particular system is time invariant when with the shift of the original signal X of N, we will get the output, same output shift in the signal Y of N. Okay, like we can say that if there is a, if I'm having time shift of K in the input signal, so K is nothing but the sample time delay, sample period time delay. Shift is nothing but the time delay. So at the input side, if I'm having some shift, some time delay in the input signal, which is represent like this, x of n plus k. Now, if this system is time invariant, in that case, what I will get? So I will get same shift in the output signal. So I will get same signal shift. That means you can say my output signal will be y of n plus k. Okay. So thus this plus k is nothing but the time delay. Okay. So most of the time for samples, we will use this k notation, time delay in the samples. This will be represented with the k. Okay. So this is the time invariant system. Now, this is the simple example of time invariant system. Okay. Now, I'm having some linear time invariant discrete system here. I'm applying this input x of n to this system, and I'm getting some output y of n. Okay. Now, this y of n is nothing, I'm saying this is minus of x of n by 2. So I'm saying that I'm getting output of this from this system, which is negative of half of the input signal. Okay, minus 1 by 2 into input signal, that is negative half of the input signal. Okay, now suppose I'm having this x of n signal, which is represented like this. Okay, this is discrete signal, but you can say this is just a sine waveform, you can say. Okay, which is having 1 as the amplitude, and this is total one cycle time period is nothing but 14 sample. Okay, and as a output, what I am getting here, this is the minus of half of the input. So at 0, it is x of n is 1. Therefore, at 0, y of n is minus of 1 by 2, that is minus 0.5. Like that, you can calculate for each sample. And you will get this type of signal, discrete signal. Okay. Now, if I put some time delay, sample delay in the input signal like this, you can say we are having k is equal to 4 here. Delay of 4 samples. Okay. If I am having delay of 4 samples on this in this particular signal, and this signal is input to this system, and then in that case, if you are getting output like this, now how to plot this y dash of n? Y dash is nothing but the y of n plus k. If I'm saying this x dash n is nothing but the x of n plus k, and here k is nothing but 4 sample period. Okay. So this sample is delayed with the this signal is delayed with the 4 samples, and this is represent like this. Now, if you plot the output for this signal, so at 0, this is 0 by 2, that is 0. At 1, 2, 3, you will get same. At 4, it is 1, therefore you will get minus 0.5, and it is again repeating. Okay. Therefore, if you are getting this type of signal as output, which is nothing but you can see here we are having the same time shift in the output signal, then this system is nothing but the time invariant system. Okay. So like this, we can identify even how whether this particular system is time varying or time invariant. Okay. Now, there are very important properties of this time invariant system, like linear, very important properties of basically the systems. So these are the very important properties: linearity, causality, and time invariance. Okay. Now, in this case, basically, if we talk about the linearity of the system, in that case, okay, we'll see later. Now, basically, how the system is basically, we define this as a something that takes an input signal and produces an output signal by some transformation. So this transformation rule is, we can say this TR is the rule of transformation rule. So if I'm having some input x of t to the system, so output y of t of the system, I can write like this. Y of t is nothing but the TR into TR on the x of t, TR in bracket x of t. This is how we can represent the system information. Okay. Now, suppose I want some system where the input signal to be doubled, or the output signal to be doubled as the input signal. Okay. So doubling in terms of amplitude. So for this type of signal, we can define the transformation rule like this. So we can say that y of t is nothing but 2 times x of t. So this 2 is doubling, that is the transformation rule for that particular system. Okay. Now, for every system, these are the 3 critical characteristics. We can say, rather properties, we can say these are the critical characteristics for any system. So what are these critical characteristics? One is the linearity, then time invariance, and the causality. So these are the critical characteristics. Now, what is the linear system? Basically, the linear system are most easy to analyze analytically. Therefore, most of the time, we prefer to deal with the linear system. Non-linear system will be very complex. So that is a different thing. But linearity is important. Then time invariant systems, which allows to treat the system input-output relation independent of the absolute time. Okay. And the causal systems, which ensures that the system can be realized in real time since the system does not use information from the future. If any system which will not use any information from the future, then we say that particular system is causal system. So these are the very critical characteristics of any system. Okay. Now, what is this linear system basically? So the rule of linearity, we can say that the linearity describes the effect of system by separating the input signal into the simple parts and using the superposition at the output to restore the overall system output. So for linear system, superposition is very important. Superposition theorem we use. Now, what this statement basically says, linearity describes the effect of system by separating the input signal into the simple parts and using superposition at the output to restore the overall system output. Okay. Now, suppose I'm having some signal, input signal x of t, and I am separating this signal into x1t and x2t. These are some simple parts of the signal x of t. Okay. Now I'm having this x1t, x2t. So I'm doing some scaling operation on this signal x1t, x2t, and after applying some transformation on this, what I will get here? So this is scaling will be A and the transformation on each signal plus the operator B into transformation on that particular signal. So we can restore this particular signal overall system output using this. Now, with a very simple example, we can see here. Suppose I'm having x1t is equal to sine t, and x2t if I'm having t, which is periodic with respect to this. Means from 0 to 2, I'm having this x2t. Periodic with 0 to t means what? This is time axis. 0, 1, 2. If I say this is varying with respect to t, therefore from 0 to 2, I am having this is t, and this is repeating periodic. So like that, like this, we can plot this signal. Okay, this is having amplitude of 2 because this is t is 2. Okay, so this is the repeating sequence. X1t is sine t, sine wave. You all know how to represent sine wave. This is the sine wave. Okay, now this is x1 and x2t. And suppose, for example, I am having one system, and this system I say is y of t is equal to 2x of t. Okay, so this x of t is nothing but combination of x1t plus x2t. x1t is sine of t and x2t is t. Okay, so in graphical form, if you plot these signal, so x1t is, you can see in this blue. So x1t signal will be look like this. Okay, and x2t signal will be look like this. You can see here in green. Okay, now if you add both signal, what you will get? What you will get? You will get the signal which is shifted on this t. Okay, the addition of this signal, please look at this graph. The addition of this signal is nothing but what? Is nothing but, you can see the output in the red form. Okay, system which will give the output as the twice of input. 2x of t means the output is twice of input. Okay, now in this case, first what we will do, we will transform x1t. We will apply transformation on x1t. So x1t is nothing but what? Sine of t. And transformation rule, what it says, it is twice. You should get the output signal as a twice of the input signal. So therefore you can see here the x1t signal is like this, which is having the amplitude of 2. Here it is 1. Please say this is 1 sine of t, and this is 2 sine t. 2 sine t means we will be having amplitude of 2. Therefore it is 2. Okay, now again this separate transformation rule we will apply on the second signal, that is x2t. So how x2t will represent? You will get this should be x2. So x2t is nothing but, earlier we will be having 2 as this, then you will get 4 as a slope. Okay, so the x2t signal after transformation you will get like this. Okay, now if separately you add this signal, if you add separately, what you will get? You will get that your signal is shifted on this. Okay, so this dash line, black dash line, is nothing but separate addition of the transformed signal. Okay, now if if I add this signal first, and if then later if I apply the transformation, say now on in that case what you will get, so that also we need to check. So 2 of x1t plus x2t, what you will get? 2 of x1t plus separate 2 of x2t. Okay, so which is nothing but the separate rule of transformation. Okay, now in that case if you add first and then if you apply the transformation, you will get the same signal on the like this. Okay, so we can say that this signal is linear because this is overlapping. This and this is overlapping. Therefore, this system is linear system. Okay. Now, this is a simple example of linear system. Now, if we take some other system like y of t is nothing but the x square of t. So whether this system is linear or not, so how to find out? So we can apply the rule of linearity. So what the rule of linearity says, so we are having the same signal and this graph is known. Now if I apply the separate transformation on the first x1t and x2t, if I apply transformation on x1t, so what I will get? This is square of the signal. So you will get like this waveform like this. Okay. If I apply transformation of this x square t on this, what you will get? You will get like this. Okay. Now, in written also, I can say x1 t plus x2 t. Transformation is nothing but the square of the signal. Now, this is if I apply separate transformation on each particular signal. So whether this is equal to this, so it is not equal to this. Basically, this is not equal to this. In mathematical form also, we can say that this is not equal. So what I have done here, basically, first I have applied the transformation on addition of both the x1 and x2t. And here on the right hand side, I have said the separate transformation on this x1 and x2. And this is not equal. Therefore, this system is not a linear system. Okay. Again, the third example, if I say I'm having a signal, the system which represent like x of t minus 2. Okay. Now, if I apply separate here transformation and then add, then what I will get? This curve, you can see black curve. And this, if I apply the transformation on the addition of both signal, so you will get this red curve here. And both the curves are overlapping. But in the previous case, you can see this black curve is not overlapping with the red curve. Okay. So we can say that this system is also a linear system, right? Are you getting my point? Is it clear with the linearity, students?
Yeah, doctor. It's all clear.
Okay. So the superposition uh, theorem we should satisfy here. Okay. So this is about the linearity. Okay. Now, in the next class, basically, we will talk about the causality of the system, time invariance of the system in more detail with some examples. Now, we will do also some MATLAB exercise for this plotting later. After, I think, 2-3 weeks, we will see how to plot these in the MATLAB. So this also we will see later. Okay. Now for this course, we can use these textbooks. Okay. So you can follow this textbook, Antonio Digital Signal Processing, and this. So what uh, I basically suggest to read some initial chapters of this book to get more to know more about this digital signal processing. Okay, so please read some initial chapters read these two books, initial chapter of these two books also. Okay.